So we're looking at page 15 in the Unit P packet, specifically number 14, r equals 6 times the sine of 2 theta. So for this kind of problem, again, it's just like the ones on the previous page. We're looking for a convenient relation, specifically having to do with that sine of 2 theta. So something that is convenient for sine of 2 theta if we're looking to plot it by hand. All right, so when we make our table of values here, we're going to have theta as the independent variable and r as the dependent variable. And so quadrantals are always a good choice, but some of the other angles along the way need to be taken into account. Otherwise, we're not going to have a reasonable framework. Now, we learned on the previous page, or we reviewed on the previous page, that the y values in the unit circle are the values for sine at a given angle. Now, what we want more than that is, or are, coordinates that are convenient for the sine function, specifically for twice the value of theta. All right, so let's say, for example, theta was 30 degrees. 2 times theta would give me a 60. Would that give me a convenient value for sine? At 60, no, not so much, right? So what I would want are values that would end up after we have doubled a particular angle, giving us those convenient angles for the sine function. All right, so those are the ones that are non-quadrantals. The quadrantals tend to work out, not always. There are some exceptions, but in most cases they tend to work out. But if you think to yourself that you're going to have twice some angle giving you a 30, then it would make sense that we would be working with a 15-degree angle or a pi over 12. Right? So that's something to keep in mind. So when we go back to that previous page, if I could not overshoot it for a change, we would be thinking that we want, I would love for this to be a 30-degree angle. Or pi over 6. All right, the whole 2 theta, not just the theta. All right, so if 2 theta is going to be 30, then theta itself must be 15. But let's not jump the gun. 0 would be a nice place to start. All right, if you double 0, twice of nothing is still nothing. Sine of 0 is 0, so 0, 0. All right, so then my next one would be, on the previous page we worked in radians, so I might as well stay with that theme, pi over 12, because if I want a pi over 6, then I would just chop it in half so that it becomes a pi over 6 when I put it in here, when I put that pi over 12 in for theta, it becomes a pi over 6. Sine of pi over 6 is equal to 1/2. 1/2 times 6 is equal to 3. All right, the next one up would be, well, I would want it to be pi over 2. All right, that's where the iffiness with the quadrantals comes into play, because 0 worked fine. But if I want it to be pi over 2, then I would need a value that is half of that quantity. So I would need pi over 4. Pi over 4 doubled is pi over 2. Sine of pi over 2 is 1, and that gives me a 6. And this is only so that we get clean numbers. I mean, you work with any theta that you want if you're fine with working with hideous decimals. All right? And some people are, and that's okay. All right? The next nice value around the unit circle that I would want would be 5 pi over 6. But again, I want 2 pi to be equal to 5 pi over 6. So 5 pi over 12 is what I should put in for theta, because when I double it, that gives me 5 pi over 6, which has a sine value of 1/2. 1/2 times 6 is equal to 3. The next nice value I would want would be pi, but again, in order to get 2 theta to be pi, I would have to plug in a pi over 2. All right, so sine of pi, 2 times pi over 2, pi, would be -1, so that would give me a -6. All right, Now, one thing that you can do is start plotting as you go and see where it takes you. Because if you know the structure of the classical curve, then after a few points, you might get a sense of what it is that you're aiming for, and then you can go from there. I'm just going to keep going with this relationship because the next one I would want would be 7 pi over 6, so chop it in half. Once you come up with a trend, you start getting an understanding that this should be 7 pi over 12. Next one I would want would be 3 pi over 2, so chop it in half, 3 pi over 4. The next one I would want would be 11 pi over 6, so chop it in half, 11 pi over 12. That's fun. All right. Although we're not actually working with those numbers because we're doubling it when we plug it in. The next one that I would want would be a 2 pi. Chop it in half, you get a pi. All right. So if I plug in 7 pi over 12, that gives me 7 pi over 6. Sine of 7 pi over 6 is negative 1/2. So that gives me a negative 3. 3 pi over 4 doubled is 3 pi over 2. Sine of 3 pi over 2 is negative 1. So that gives me a negative 6. 11 pi over 12 doubled is 11 pi over 6. Sine of 11 pi over 6 is negative 1/2 times 6 is negative 3. Pi times 2 is 2 pi. Sine of 2 pi is equal to 0 times 6 is 0. All right? So we've kind of completed the cycle because we're back to an R value of 0, which means we're back to the pole. So let's see where that gets us. I'm not going to write them as the ordered pairs because we know that we're identifying the location of theta first, and then we're taking R steps in the direction or away from those theta values, depending on whether R is positive or negative. All right. On the previous page, I believe all the R values ended up being, yeah, surprisingly, they were all positive. All right, but here we got some negative R values, so we'll have to account for that. All right, so I'll plot 0, 0. 3 steps in the direction of pi over 12. 6 steps in the direction of pi over 4, which we're calling around right there. 3 steps in the direction of 5 pi over 12. All right. 6 steps away from pi over 2. 3 steps away from 7 pi over 12. All right, so I got to find my 7 pi over 12. That's going to be really 3 steps in the direction of 19 pi over 12. All right. I lost my train of thought there. Let's see. 3 pi over 4, 6 steps away from that. So it's really, we're looking at just kind of a ballpark. Yeah. Again, right about right there. It's 6 steps in the direction of 7 pi over 4. So we're just calling that like that little space between the end of the line segment and the denominator of the radian, we're calling that 6. All right, so just try to keep that consistent and you're okay. All right, where did I leave off? Let's see, 11 pi over 12. That's going to give me, so negative 3. So negative 3 for 11 pi over 12. That's 3 steps away from 11 pi over 12, which is really 3 steps toward 23 pi over 12. All right, and then back to 0, 0 pi. But it's really 0 because the R value is 0. All right, so this looks kind of incomplete. Now, if you want to get a sense of what's going on here, R equals 6 sine 2 theta. Again, you got to type in the theta. A little aggravating, but you get there. And you're like, oh, okay, well, that looks nothing like what we just developed. Well, kind of yes and kind of no. All right, so let's take a look. If I connect these points here, poorly, of course, all right, I get like a petal of that rose. All right, this is the classical curve rose based on the model that we have. It's a little wonky over here, so I'm going to fix that. Oh, not much better. Oh, that didn't really end up being too good, but that's okay. All right, so it looks like I have some other points over here that I can work with. All right. And, you know, sometimes mistakes happen. I just realized, based off of the diagram, based off of what I constructed, that there's no way that this point could be correct. All right, so I'm going to go back. Where did I get that from? Pi over 2. Well, the pi over 6 steps away from pi over 2. So let's take a look at that. I'm being too fancy with my mental math here. Pi over 2, 2 times pi over 2 is pi. Oh, sine of pi is 0. Crikey. All right, so that goes away. Because that should have been at the pole. Oh, that's a huge 0. What are you going to do? Fix it, that's what we're going to do. All right, so with the use of technology, you can see what you're supposed to have and what we have. So you can kind of rely on the symmetry component to come up with the rest of it, or you could just keep going and so on. All right, I'm kind of along the lines of, okay, well, we now know what the trend is, and it is symmetric over the would-be y-axis, so I can infer lots and lots of points here. So why not just do that and come up with the rest of the graph that way, you know? All right, so then the natural extension to that idea would be, well, what if we didn't have the technology? Well, that's where the definition of the classical curve comes into play. So if you look at the polar equation for rows, you see you have the two forms. R is equal to a times the cosine of n theta, and r is equal to a times the sine of n theta. If you play around with the a and n values, you'll see that each one controls a certain aspect of the rows. All right, so let's actually rewrite this so that this is an a and that's an n, this and that, and then add my sliders, and then just see what's going on. So if they're both ones, it looks like a circle centered around 0. I'm sorry, centered around the y-axis. All right, so let's make it what we have here, 6, which means I zoomed in way too much. And, whoa, look at that, it's crazy. 2. Oh, if it'll let me. One thing you can do with this is you can make your step 1. So if you just tap on it, make your step 1, then it'll only go in integer values, which makes things a lot easier. So I'm going to zoom out a little bit. All right, so if you take a look at, and I could even do that just for simplicity's sake, I'll make the a value go by integers also, so that it's a little easier to see. Well, it looks like in every case, no matter what I do, it seems that it's symmetric about the y-axis. So that's good, we could rely on that. And you may look at it and say, well, I wonder if that's different for a cosine function. Well, find out. Oh, I mean, we will in a minute, but find out by changing sine to cosine and see. All right. So the question would be, well, what does the a value control? Well, this looks kind of circular, right? If you were to connect all those extreme points along the petals of this rose, in every case, you could kind of encapsulate this within a circle. So it's a question of, I wonder what that circle would look like. So let's make the circle, and we'll call it r equals a. Aha! Interesting. So it appears as though the a value controls the radius of the rose. All right, so I went out 4 units from center in my r equals a to make my circle, and the rose does the same thing. All right, so we got that. So I now know that if it's in the form of r equals a times sine or cosine, as it turns out, it will work for cosine as well, of n theta, the a value will indicate how far out you're going, the most extreme point of the petals of the rose. So now, in terms of the rose itself, so let's start with, well, 0 doesn't really give us anything. 1 gives us a circle, but you could think of that as a one-petaled rose. One-petaled rose. Let's go to 2. 2 gives us 4. 3 gives us 3 petals. 4 gives us 8 petals. 5 gives us 5 petals. 6 gives us, if you count them up, 12 petals. So we're looking at the number of petals. So if n is odd, the number of petals is equal to n. If n is even, the number of petals is 2n. So we know the radius is equal to a, and it's symmetric about the y-axis. All of this I was able to glean from just a quick analysis on Desmos using sliders. Pretty not bad. All right. So then the next one, r is equal to negative 7 cosine of 3 theta. Again, it's going to come down to whether or not you can identify clean values for cosine. So we know that the clean values, you know, just going back to the unit circle, kind of living in this unit circle, all the stuff that's highlighted in yellow, the ones that we want, I'll use a different color here. I'm going to go orange for those keeping score at home. So these are the friendly ones. Again, I'll just go with the non-quadrantals. These are my friendlies. So we're working with cosine of 3 theta. So 3 times some number should give me these friendly values. Okay, so we're going to hold that in mind. So the friendliest value would be 60 degrees. So I want something multiplied by 3 to give me that friendly value. All right. So I want this reference angle. I want this to be a reference angle of 60 degrees or pi over 3. So when I work with a table, let's see if I can do it without the computational errors. That'll be fun. I gotta be nice to myself. I only made the one computational error. So 0. 0 is always friendly. All right. So if I plug in a 0, that's not really gonna impact things too much. Cosine of 0 is 1, so negative 7. All right, the friendly value that I'm aiming for is pi over 3, so take that and multiply it by a third. Pi over 9. Yeesh. So I want to use a pi over 9 somehow. Well, that kind of poses a problem. Because I look at my graph here, I don't see a pi over 9. All right, we'll get to that in a second though. All right, so we'll just kind of carry this thought. If I multiply pi over 9 by 3, I get pi over 3. Cosine of pi over 3 is equal to 1/2, so we get negative 7/2. The next one I want would be pi over 2. 1/3 of that would be pi over 6. All right, pi over 2, 1/3 is pi over 6. So that part is fine, I guess. But cosine of pi over 6, you know, oh, I'm sorry. No, that one is perfectly fine. I went the other way in my brain. Yeah, and we could even plot pi over 6. So this is a good one. All right, so that's going to give us a 0 because cosine of pi over 2 is equal to 0. All right. The next clean one, or the next nice one, would be 2 pi over 3. That's what we'd be looking for. 1/3 of that would be 2 pi over 9. Multiplied by 3 is 2 pi over 3. Cosine of 2 pi over 3 is negative 1/2. Negative 1/2 times negative 7 is going to be 7/2. Now, before we go too crazy here, let's start thinking about something very important. And that something is, this is going to be a 3-petaled rose. All right? Because we know, and that's because I alluded to it, that a lot of the characteristics are going to be holdovers here. So let me put in the cosine function. All right? So let's just verify that I'm not lying. For an odd number, I get 1 petal. Even number, I get double. the number, whatever the number is, the n value, I get double that to give me the number of petals. 3, same number of petals. 4, double. 5, same. 6, double. Radius still holds, so we're still good there. So all this stuff that I'm about to copy over still applies. So then I just want to talk about symmetry real quick. This is a cosine function. So let's go, because it gets a little crazy when you talk about the larger values of n. Let's go with a smaller one. This does not look symmetric about the y-axis. It does, however, look symmetric about the x-axis. All right. So for the cosine function, the only difference when dealing with the rows is that you'd have symmetry about the x-axis. All right. So what I would suggest for these kind of problems, once you've identified what kind of question it is, and you kind of know all the background details, start plotting. All right, so 0 is our angle, 7 steps away. That's going to put me about right. I'm going to go a different color so it stands out, so it pops, as the kids say. Start plotting some points, because when you do, you'll have the symmetry, you'll have the number of petals to kind of fall back on. All right, so the issue that we run into is that pi over 9. Now, the good thing is, if we're working in fraction form, you can kind of split the difference, or you can definitely split the difference between the denominators. All right, so if we assume that pi over 9 is equidistant between pi over 6 and pi over 12, then we have enough information to create a new line segment consistent with pi over 9. All right, and so then we can plot 3.5 away from that. All right, so what I would do here, because I can, and what you would probably do if you're doing this on paper, is you just pop a ruler on there and extend it. But I would take 3.5 steps, 1, 2, 3.5 steps away from pi over 9. All right, so then you're 2 pi over 9. Okay, well, hold on. Before we even get to that, let's think about this. 2 pi over 9, that's going to be somewhere in the second quadrant. All right, I'm sorry, in the first quadrant, and that's fine. We can get there. All right, but let's use symmetry first. If we know it's symmetric about the x-axis, then there has to be a counterpart in the second quadrant corresponding to this one, somewhere between the 6 and the 9. And it's pretty easy, I would think, to ballpark it and come up with this petal of the rose, if I can draw without the shakiness. So now we have one petal out of, well, I'm looking for 3. All right. Now, a good question would be, okay, well, what does that negative have to do with anything? Well, take a look at this picture. I have this as 4, but I could easily make it 7. And this is what 7 cosine of 3n would look like. All right, you see that one petal is pointed to the right? The only difference is, if it's negative 7, is that first petal, it's going to be a reflection. That first petal is going to point to the left. Everything is going to be a reflection over the y-axis. All right, when you negate, you know, like in the rectangular coordinate system, when you negate a function, it's a reflection. It's the same idea. All right, so we need to ballpark where 2 pi over 9 is. That's, I put in the Desmos, 360 divided by 9 is about 40 degrees. So we'll have to estimate, well, here's 30, here's 45, separate 5, 10, 15, so 35, 40, 45. So that gives us a little line segment here that would be 40 degrees. We're going to take 3.5 steps in that direction. All right, so 3.5, 1, 2, 3.5. Now, based off of what we should end up with, that tells me I'm going to need a little bit more, but I can at least be confident that I'm not, totally botching this. All right. So the next angle that I would want would be pi. A third of that would be pi over 3. All right. So cosine of pi, you plug in the pi over 3 times 3 is pi, would be -1, so that gives me a 7. So at pi over 3, I should have a 7. So it's going to put me, if I'm ballparking the 7, somewhere about over here. So I know I'm looking at something like this. And then using symmetry, I can eyeball it and say I'm about 1.5. So I'd be living in this neighborhood over here. All right. And then we'd really be using symmetry by saying somewhere down in this neighborhood we have a point. Then, we're going away from that pi over 9. Yeah, but I mean, it's kind of like counting boxes, except they're not boxes. I would be saying, all right, how can I get to this point? Well, I'd go 1, 2, 3. It looks like 3, and then up from there about 1, 2, and 2/3. So 1, 2, 3, and then shoot it down 1, 2, and 2/3. It's going to put me right in this neighborhood over here. And then using symmetry, you can get your other point, which is going to get you over here somewhere. All right. So, I mean, we really are eyeballing it because we don't want to spend our whole lives coming up with these graphs, especially since the graphing calculators can do it for us. Oh, yeah. Look how, oh, that's just brutal. All right. Well, we got there. I mean, I can't live with that one, but. Well, I got to live with the point, right? Well, let me just kind of smooth it out a little bit. I don't know. It's never going to look good. Now, the last one is kind of putting everything together and saying, all right, well, what do we know? Well, we're going to have one petal. It's going to be symmetric about the y-axis, and it's going to go upwards, right? And so, if you want to eyeball it, you could do that just by popping in a coefficient of 8 and an n value of 1. And see, well, this is a cosine function, but it's going to be on the y-axis because a sine function would be. That's what we're looking at. So we want to go up 8 units. Six, 7, 8, I guess. It's all right to go off the grid in my mind when it comes to this stuff. We just need another point. All right, so we need a point that's convenient for sine. All right, so let's go with r equal, well, that's not a marker, r equals 8 times the sine of, I guess, pi over 6. That'll give you a 4. All right, so 4 steps in the direction of pi over 6. If you use 5 pi over 6, same deal. That gives you a couple of points. If you want to go with other points, you can, but we have enough where if we just draw a circle